Okay, I set up a egg and chalk. Where is it? Egg and chalk. We have to go to spot colour on this. Egg and chalk, and then we come back here. 48 hours, it looks like it could possibly be pinking, which means then the red organism, is probably not greatly affected by the calcium. Hopefully we've actually converted the calcium to a different form. Which one it is we don't know at the moment, but eventually we'll probably have to do a whole series of chemical experiments to find out which form it is. This one here with the manganese dioxide that was just sort of going down. Let's go back to spot colour. Going down on there. It's now starting to pink further down, but still isn't. So it's still in the top region. So if we added something like molybdenum to there, it will probably descend much faster, as we've learnt from other experiments. So okay, this one is pinking, but again it's doing very. If we can get back to spot colour again, if you can see, if we move this out of the way, it's very localised, and you get spotting and all sorts of things like that, and also getting this like black band around the top as well, which I assume is probably manganese dioxide, because I'm working on the principle now that the manganese dioxide probably sequesters and therefore over time accumulates this different form of calcium. So then when you see the flytraps growing in this sort of black sandy soil over in North Carolina, they're probably growing in a surface layer of manganese dioxide, which attached to that and accumulated to that over time is our special form of calcium, a different form of calcium, which basically separates the Mexican pinguiculus from the ordinary pinguiculus, I would suggest. Because the Mexican pinguiculus can handle calcium when it's granulated. They can handle chalk when it's granulated, and they can also cope with copper, which is unusual compared to all the other CPs, which apparently have a problem with copper. But we're going to do another definitive experiment today, mainly because if you look through this, all these pictures in this book here, if you go through page by page, all these fly traps seem to have this sort of glowing green colour to them. So if you go through this book, and they all have this sort of strange glowing, probably have to go to spot colour. They have this sort of strange glowing sort of colour to them. So if you go down there, and they all have this sort of glowing yellowy green sort of colour, and and some of these things here with the stems sort of match the colour of the stems. I'll put that to one side. In Donald Schnell's book of cultivational, where is it? This sort of stem look there sort of matches a plant that you see in the wild there. So if you go through these books, you can see them. And of course, then you've got this classic one in the original Schnell one, having somewhat of this washed out sort of mixing toothpaste with the chlorophyll green of grass sort of look. But anyway, enough of that. What my task today to do is to make up a egg copper chalk one, and we'll see if we get a difference. So the idea is to grab the old tripodus, and we will do exactly the same, but now we'll add the copper after we've added the chalk to the egg. And you'll notice there is a difference with the chalk. It doesn't quite go as lumpy as when you add the copper, so we'll see if there is a difference later on. Okay, just get everything in shot, because there's nothing worse than being out of shot. So okay, I think that's about it. Good enough. So stage one, grab your egg, standard, I'm going to call it a 900 gram egg, That's what they call them, I think. 6 to 900, I think it's a 600 gram egg. But, okay, so basically we're going to get our yolk here. Maybe I need to go on to spot colour. I am on spot colour, bugger. Anyway, so we're going to get our Am I in screenshot? Okay, out here somewhere. And we're just going to quickly do that to the egg. And then we're going to get our known quantity of, that I know from experience over time that this will, and we'll put that in, so that's our chalk. And we're going to mix that in slowly. You can actually slowly mix this in. And it will slowly pick it up, and you will notice that it also the egg starts to react with it. So I'm assuming it's because it's a reductive protein, it will be doing its. We're still in the shop. Yeah, it will still be doing its reductive capabilities, but on the chalk. So we're probably creating a different form of valence calcium, and this I'm assuming that this valence calcium will actually stick to manganese dioxide and accumulate in the manganese dioxide. So therefore it accumulates and doesn't go anywhere and be in like the surface somewhere in one of the surface horizons, if not the top layer. But you can play around with all this. So because the manganese dioxide doesn't interfere with our organism, this doesn't appear to, at this stage, interfere with our organism. But I'm just wondering whether when we add the copper, we will get that sort of, eventually, when we get cyanophyta growing, we'll get that sort of glowing green thing. Because they talk about iron or air being the emerald isle. So what I'm going to do, I'm going to get my copper, as you do, and I'm going to take my spoon of copper there, and I'm going to put this to one side, because I want you to see if we get any reaction here. Now, make sure it's in shot. Okay, now I'm going to add our copper here. Now, is it going to go green again, or is it going to stay blue? So is the copper going to be trapped in the calcium, attached to the calcium, but of course the calcium will be in a different valence state due to the reductive nature of the egg. So this is the difference between people talking about trying to grow lichens and moss on their walls using milk and yogurt when they should actually be using egg, because that's a reductive protein, whereas the milk, and also when milk goes off it forms lactic acid, which is very acid. We know that our organism doesn't like being too acid, but I said I'm going to do that experiment again with 1/10 of the amount before. Yeah, it is starting to go green, so it is reducing the copper, which again implies that it's probably reducing the calcium, but it could be some sort of redox thing where one goes down and one goes up. Whether this can also keep pushing it down until it becomes a much more reduced form, a brown form, which is why peat is brown, I don't know. It's not really due to all the so-called tannins. Anyway, I think that's enough. I don't think we can do much more with that. I think we've got it there, fellas. Now, we're going to take our bottle here, if we're still in shot. I don't know if we want to go in any further. Maybe we can go in a little bit further. And we're on spot colour there. A little bit more. And we're going to probably try and get this to go, get my hand out of the way, in to the container. So now we've hopefully got a reduced form of calcium that the copper appears to be attached to, but it may not. We'll find out if it separates out but still stays green. We'll know whether we're going to get a bloom eventually of our red organism grows and then goes green, but it goes to a particular green matching the colour of some of those wild shot photographs on the plant. See, the thing is, can this actually go round and take the place of the calcium pectate around all the cells of the plant, this particular form of reduced calcium? And maybe with the copper attached to it give you that sort of glowing green. But at the same time, does it fix nitrogen from the atmosphere? So every single cell of the plant is being surrounded by this special form of calcium that can also fix nitrogen from the atmosphere. And of course the atmosphere is very close to those cells on the outside. So that will give it an ecological advantage. It can move out, the plants can move out into saltier, more organic rich soils, because remember it's the 2-to-1 ratio between organics and salts again, and also manufacture their or absorb their own nitrogen. So of course that begs the question, why are they carnivores? My suggestion is they're eating the insects for the potassium so they can cope with this salinity.